that being said, we're 2 minutes after the hour, and let's get started. Today's webinar is how to reduce production incidents and outages with machine learning. And I know what many of you are saying, oh no, machine learning, let's play some buzzword bingo. And I think our slide here shows it. You know, we've all, unfortunately, have been desensitized with what we've seen and heard from various vendors, players, and even websites and media sites regarding some of the words that we see here up on the screen. Big data analytics, streaming analytics, neural networks, sensors, so great. Blended analytics, and of course big data, maybe one of the most overused words. Doesn't mean though that these words have no meaning or are not relevant or not valuable. It just means that perhaps we've been desensitized to them. And we are going to learn, we're going to focus today on machine learning and how it is important and how it is relevant. And we hope you guys will learn from this. We have two great panelists for today's webinar, and let me introduce them. So first, the guy in the big funny glasses is Steve Burton, VP of Product at MOOCsoft. And, you know, before he put his glasses on, Steve also was at AppDynamics, Glassdoor, and Precise Software. Steve, I just want to make sure you're there and hear us well.
Yeah,
welcome
everyone.
Thank you. And then our chopper rider here is Richard Whitehead, CTO of MOOCsoft. And again, Richard, while not riding, is formerly an advisor at Splunk, Micromuse, and EMC. Richard, welcome to today's webinar.
Thanks a lot. Great to be here.
Okay, that was my sound check. Sounds good. Guys, I am looking forward to this. This is a topic that I find extremely interesting, and I'm sure our audience will as well. I'm going to turn it over to you now, and we'll sit back and learn and listen.
Thanks, Alan. Welcome, everyone. This is the agenda I put together for the next 50 minutes. I'm going to do the introduction and set the scene about why machine learning is needed, first and foremost, talk about production incidents, and then its relevance to IT operations. And then the second half is going to be Richard talking about machine learning approaches, some of the algorithms that are being used or can be used. And then also he's going to close with some real-world examples where machine learning has been used in some of the biggest enterprises today. So with that, I'm going to get started. I wanted to start with one kind of big statistic. This was actually a big shock for me. I've spent the last 10 years in the monitoring space with lots of different vendors, and if anything, for me, this slide was pretty disappointing in the fact that the majority of today's incidents are still detected by end users. So despite all of these new tools coming along and being able to spot and detect things are still not where they need to be with regards to how fast operations can detect incidents. And obviously, like most of the incidents you see here, 74% are actually detected by end users. And what this means is you get lots of tickets, you get lots of incidents, and all of those things results in lots of labor and costs for people to try and resolve and troubleshoot these incidents. So that for me. I wanted to start there and just really set the scene for what the world looks like today. It actually happened to me last week. I was trying to book a flight, went onto a website, and literally clicked book, and this is what I got. It was, whoa, something broke, please call this number. And guess what I did? I went on Twitter and ranted because it's like 2016 and I still have to call someone to book a flight. And the result of that call was 20 minutes on the phone going through with someone on the support help desk manually making a booking. And this thing's happening like every day. Every hour, something will break, people rant on Twitter, and guess what? All of these things get logged as tickets and incidents, and it's a complete nightmare for IT operations. I actually started my career on a help desk for a travel website, which is kind of ironic given this slide. And it was the same thing. My job was to literally listen to people who were annoyed and book tickets. What's also interesting about these tickets is that a lot of them are a repeat incidents. So nearly 35% of all incidents today are either duplicate incidents or the repeat incidents, meaning they've happened in the past. We actually did a survey at MOOCSoft when we attended one of the big monitoring conferences last year, and we asked attendees like what percent of your incidents are repeat, and this was the results we got. What's kind of important about this is the repeat incidents also create a lot of tickets, a lot of labor and cost, but also the fact that 2/3 of incidents are unique, this makes prediction really, really difficult. And we'll get to why it's difficult to predict things in a few slides. Last week, spoke to one of the biggest banks in the world, and this is what their VP of Ops said. We create 90,000 tickets a month. And he's like, yep, 80% of them are complete crap. We know it, but that's the way things are today. And each ticket still requires someone to go and triage and close the ticket. And this isn't just what we've heard in banks. Like, this is pretty much every week what we hear from customers who've got these network operations centers, these help desks, and they're almost just creating tickets because they have to. So just kind of bear that in mind. My first boss, when I was on help desk, said, you'll make mistakes, that I can guarantee. The most important thing is whether you can actually learn from those mistakes. Quite ironic, given that this was my personal experience on that help desk. I was pretty much, all I was doing was restarting servers and processes. And it actually worked, right? This is what most of us in IT are used to doing is let's just restart the server. Even from our days using a PC, if Windows broke, we just restarted it and it worked. And yeah, so what I didn't really learn on help desk was like, what was the root cause? Like, what was causing these problems? And so what I've got here is a timeline of the technology trends that we've kind of been through all the way from the mainframe era when I was born. Can't believe people and colors were that in the 80s, but there we go. And what you see is as we go through the decades and the technology shifts and the transitions, two things actually increase. One is the number of tools that we buy. So for every technology, we typically buy another tool to monitor that technology, but also the number of events, the alerts and the metrics that IT operations actually consume increases exponentially. And right now, everyone's talking about Internet of Things and microservices. We're actually at a point now where IT has billions of events, alerts, and metrics. So we all like to buy new tools. I like tools. I like playing with monitoring tools. That's been my life for the last 10 years. But as a result of that, those tools create lots of data for IT operations. So what I want to do now is just do a quick poll and kind of understand from you how many monitoring tools you typically have today in your organization. Jules, can you open up the poll, please?
Here's our polling question. How many monitoring tools are you currently using in your environment? And if our attendees would select one of the following, shouldn't take you too long, I hope. And we will close voting in 5, 4, 3, 2, 1. And the survey says, wow, 66% with more than 5. Guys, I don't know if that was what you were expecting. 3 to 5 at 28, and 0 to 2, only 6%.
Yeah, that's correct.
Yep.
So that kind of confirms where we're at today, 2016. And as a result of having multiple tool sets, we've actually become a data dog. So like all of us have become dogs that look at monitors and different tool sets. You might have heard of the eyes on glass approach to monitoring. And this is for a lot of IT departments and operations, this is typically what happens where you have different teams, different tools, and people are looking at eyes on glass. And then when something breaks, all hell breaks loose, and everyone starts shouting. Lots of alerts get fired, lots of events, lots of metrics, and this is the reality for a lot of teams. And what it means is you now have to manage millions of possible events, metrics, and alerts to try and troubleshoot an incident and really understand what's going on. And this is kind of what it looks like if you were to kind of visualize all of that madness. It might look like this. So you might have, for example, Nagios, you might have loads of hundreds or thousands of critical alerts on a dashboard. You might have an event console that just glows red. A lot of customers use event consoles and all the events come in, and it's down to operators to kind of figure out where things are broken. Or you might actually have an where thousands of events get applied to, and no one really talk about. Let's monitor everything. Like, that's great, but if you can't analyze all the information, it's problematic. The bigger problem is also the fact that most tools that we own today don't actually analyze the information they collect. And let me give you a few examples of that. They actually rely on humans to actually do the analysis. So for example, a log analyzer tool, it might collect all of the log entries, all of the events and the exceptions in log files. All that does is collect that information, index it, and make it available for users to query. So it's still the users that have got to put in the queries, figure out which machines, what metrics, what type of events, and whittle it down to try and get to the root cause and troubleshoot. Other tools that try and aggregate a lot of the metrics, it's down to you, the end user and the operator, to actually create your own dashboard. Like, give me this metric, give me that metric, right, slice and dice it on this server, this part of Amazon, give me this view. And like, this is all down to the user to try and find where the issues are and detect the anomalies. And the reality is, in today's world where you've got billions of metrics and events, like that's a never-ending task. Here's an example that I met with a customer about a month ago. They have 4,000 applications in production, 60,000 servers, over 15 different monitoring tools, and this was how their operations team did anomaly detection. They had 75 operators, I think 35 were in India and 35 were in the US, and they manually analyzed 30,000 events a day. That was their job. And roughly 3% of those events were ticketed as tickets and incidents and being managed. And actually, like, if you look there, like only 9% of those incidents were actually detected by tools. And this is what, again, what we see every single week when we meet with enterprises because of the operational volume and the operational noise. And this is why, like, if you want to reduce production incidents and tickets, like, there needs to be a better approach. So if you think of like good old Homer at his console, like the old way, and now the new way. So there's actually a way you can help and average machines who can learn, who can automate a lot of this human behavior. So here's a definition of machine learning for IT operations. This is from our founder and cow lover. So if you notice all the cow logos, that's just because our CEO is obsessed with cows. And you see here, class of methods to analyze data, to iteratively learn from the data, and find hidden insights without being explicitly told where to look, in real time and at scale. And I think the last two are important. If you've got all this information, you need to get the insights in seconds. You can't really wait minutes or hours, especially production incidents where every minute of downtime is so expensive. For all of you that love Terminator, unfortunately this isn't machine learning, as great a movie as Terminator is. We'll get to what machine learning is in just a few seconds with Richard. But it can help IT operations. The first thing it can do, it can reduce the operational noise. So instead of looking at millions and billions of metrics, machine learning can actually analyze all of the signals pretty much in milliseconds. as they come in on the fly from different sources, and that's really important. The less noise and the less events and alerts that you see typically translate to less tickets and incidents that you'll create. Second is detecting anomalies. Again, being able to understand what is normal and abnormal, looking at a huge kind of volume of events coming in and looking for relationships and patterns, which kind of gets us to the next kind of third big point. Understanding the real relationships between the metrics, the events, and the alerts. If you can do that, you significantly reduce the duplicate tickets and incidents that your teams will create. And some of the examples Richard will walk through will kind of tell you why this is really important. And then lastly is closed loop remediation. If you can learn from the incidents you've had in the past, you can use machine learning to detect similar incidents and help you automate those remediations or come up with suggestions based on what's been observed in the past. So these are really the 4 key areas that machine learning can help IT operations. Here's an example. So let's imagine this is your IT infrastructure. You've got millions or billions of events all there, and it's down to you to figure out which ones are anomalies, which ones are related. What machine learning can actually do first is it can reduce the number of events. So it can do deduplication, it can do blacklisting, it can throw away the events that are not relevant. The second thing it can do is it can understand the relationships between the events, the alerts, so that you can kind of get an understanding of like what is the patterns and relationships there. The third thing it can do is it can detect anomalies, and it can help your teams create a small amount of incidents versus creating hundreds of tickets or thousands of incidents every month. And I've just walked through kind of very simply what machine learning is good at. It's good at taking lots of information and boiling it down to a few kind of tens of pieces of information that humans can then action and work on. With that, I'm going to hand over to Richard now, who's going to define what machine learning is and then talk about how it's applied in IT operations and give you a few customer examples.
Thanks a lot, Steve. So this is great. So my antidote to the Terminator is I give you Alan Turing. He's not quite as shiny as the Terminator, but he's generally considered to have saved Western civilization, so that's not too shabby. So before we get started, the first thing we need to do is, since the definitions and buzzword bingo has created a very subjective definition, I figured we'd just do a really quick recap of the terms and how we use them in our context. So when we talk about machine learning, we talk about supervised machine learning, and that's where you tell the algorithms what the objective should be and let it figure out how to get there. Semi-supervised, which is a little bit more controlled, where you nudge it in the right direction and provide it with additional information to speed up the process. There's unsupervised machine learning, which is probably one of the areas of greatest investment in intellectual research, where you're basically feeding data into an algorithm with no structured model, no tutorial, and let it figure out information from the data set purely. And then there's the notion of reinforced, where it's a little bit of both, but what you do is just nudge it in the right direction by saying, yes, this is a good answer, no, that's a bad answer, and help tailor it. So that's how we use those terms. And the bulk of the intellectual property for our company and the contributions to research and mankind in general from our founders really falls into the first 3 categories. So one of the things that we've observed when you're applying this kind of academic research to real-world solutions is that one size does not fit all. A couple of things about what machine learning isn't. Machine learning just isn't predictive analysis. That's an area where a tremendous amount of products have come into the marketplace and a lot of focus has been on them in the past, but that's only one niche sort of area of research. The reality is it's incredibly difficult to predict things that have never happened before based on data. It is very good for capacity planning and load and so forth, but it's not very good for detecting issues that are unpredictable. You can never predict a backhoe going through a fiber bundle, for example. Machine learning probably isn't a good environment for solution for small static environments, really, because it's probably just as easy to write a couple of rules than it is to deploy machine learning. Machine learning does work very well in large dynamic environments. You get a better bang for your buck in those environments, and you also have the best chance of seeing things that you didn't predict. And that's half the fun of machine learning, to be honest. In short, machine learning isn't a silver bullet. Also, it's not going to be 100% correct all the time. There's a little bit of fuzziness there, but that's part of the value. And you need to be able to relax the constraints, and that's a phrase you're going to hear quite a bit, I think, as we progress. So we're also going to talk about some types of machine learning algorithms. These groups here, the 6 here, are primarily focused on the area of clustering, which is a form of algorithm that we use extensively. And we'll step through these. They're worthy of a little bit more interest. The first one is time. Now, time's great. Time's probably the most common algorithm. In some cases, it may not be an actual algorithm. It might be something that you do, just cognitively when you look at things. Anybody who's ever overlaid two sets of data points on a graph, that's time domain correlation. You see it a lot in tech support. The two most common questions you ask when somebody calls in with a problem is, what did you do? And the other one is, what else happened at the same time? Both temporal relationships. What we find, though, is when you look at real-world implementations, they tend to be focused on retrospective solutions. So forensic analysis, looking at past information. Very few solutions in the marketplace are working in real time, and that's where we focused our efforts. So one of the downsides of pure time-based correlation is the opportunity for coincidence. So sometimes something just happens at the same time, and that doesn't necessarily imply a real relation. And we'll talk a bit about how you mitigate that. But first, we'll come back to that relaxing the constraints. Why is something as loose as time so powerful? Well, it's because it's entirely data-driven, and that's really valuable. This just 2 data points that I put here. The pink line going down is a measure of the available IP addresses, IPv4 addresses, and that's just an indication of the explosive growth in internet devices out there. So it's a measure of scale and growth. The yellow line is really intriguing, which is a measure of the available tools and solutions and products in the marketplace to monitor your environment. And I've personally been around long enough to notice this and see that massive spike in recent years. So a proliferation of tools, which is why we weren't in the slightest bit surprised by the survey results. And what that means is you can't possibly keep ahead of all of these potential solutions. You can't write static models for every conceivable environment. So that's why we relaxed the constraints. So the second technique for clustering was linguistic. This is basically the application of natural language processing to your data. Again, another very data-driven solution and very powerful as a result. In practical terms, what we've done is we've created a lexicon of terms that you would likely find in an IT environment. NLP is not a new technology by any stretch of the imagination. And you could argue that what we've done is we've created a lexicon that speaks fluent Loglish, because we're looking for keywords and patterns that pertain specifically to IT use cases. And I had to pick an example for this, and I've chosen one that's actually fresh off the press. This is a screenshot I took yesterday, where we're actually processing something that is arguably an excellent form of an example of natural language in an event format, which is a tweet. And what we've done here is we're ingesting tweets and looking for patterns and relationships in terms of service providers and potential outages. And outage is a good keyword to use. And what we're able to do here is create situations dynamically, even without understanding who we're looking for. And the example shown here is we captured 39 tweets of some potentially outraged customers concerned with the availability of a particular service provider. So this notion of clustering related alerts together and pieces of information, very, very powerful because it is so data-driven. An example can be that if you identify sufficient patterns across your infrastructure from the data, you could, in theory, reverse engineer the relationships and dependency. So it's the opposite of having to create a static model. So data-driven, very, very powerful. since we're talking about things that are data-driven, I'll talk a little bit about time as well. Again, because so many analytical processes tend to be retrospective, time's very, very important. The further back in time you go, the richer the data becomes. Well, I'm going to offer a corollary to this, which is in a rapidly changing environment where things are unpredictable, learning for too long can actually be counterproductive. So to use the analogy of the smartest goldfish in the bowl, we use the goldfish's much maligned memory as an example. So whilst the goldfish can understand what's going on, one quick circuit around the bowl, he's forgotten everything. And that's essential if you're dealing with a rapidly changing environment where virtual machines have been provisioned, stood up, torn down in the time it takes to essentially model your environment. Networks are rapidly switching, load balancers are fluctuating. But the point is, once that circuit around the bowl has been completed, the goldfish immediately analyzes and understands the environment accurately. So another technique is topology. Now, gosh, topology could be the subject of an hour-long webinar at least on its own. So, well, we'll just sort of cover this one very rapidly. The point here I'd like to make is that topology doesn't just have to be network. Topology can be any kind of representation of relationship that can be described in the form of a graph. So it could be things like you could extract it from a CMDB, it could be the relationships of servers and storage arrays and so forth, any kind of dependency that can be described that way. And for those of you interested in this particular subject, stay tuned because we've got some interesting stuff coming down the pike in terms of some patents that are pending regarding graph entropy, where we're really looking at how can we mitigate the issue of the reliance on a static model and still leverage topology information from an environment, but in a nimble, scalable fashion. So stay tuned on that one. Operations template, well, this is a more static solution. This is where your operators have the ability to essentially say, I know exactly what I'm looking for. Maybe it's something that's been generated by an algorithm, and you want to say, yes, that's really awesome. I want to see that immediately the next time it happens. Very powerful, a great way of rapidly reusing intelligence. Neural feedback, well, this pertains to neural networks, which is yet another technique or sort of embodiment of machine learning. In this instance, we're really basically acknowledging that unsupervised algorithms only get you so far. The human element is absolutely critical. You need to be able to adapt and modify these algorithms on the fly. So what we're doing is we're observing operator behavior. When the operator corrects an algorithm or improves it, you need to be able to capture that information, essentially build the neural networks, and allow optimization for the future. Examples in a practical sense would be when you learn operator behavior, such as merging clusters, splitting or creating clusters, annotating, adding additional information, anything that indicates the importance or increased or decreased value of an algorithmically derived cluster is an opportunity to learn and improve. The other technique we referred to, this is kind of a name that is kind of peculiar to us, is the notion of Cookbook. And this is very much a semi-supervised form of clustering. We're still using unsupervised machine learning, but what we're doing is we're very specifically directing it in terms of what you're looking for. So, for example, if you're an environment and you're really interested in geographical location, that's the most important piece of operational value to you, you can specifically focus the algorithms on geolocation or labels that indicate data centers. So it provides maximum control, but at the expense of a little bit of effort, but they tend to be very reusable. So it's a bit like artificial intelligence. You're applying your domain knowledge to provide a much more accurate and focused form of analysis. And since we talked about these different techniques, I like to look at it in terms of the value chain. Some of these techniques provide great value, but only for a short period of time. And an example would be one of our techniques is to provide a significance value to an incoming message. That's something that is basically something that occurs very rapidly. In fact, to go back to the goldfish in the bowl analogy, all of the learning that we do, we tend to throw away, I think by default, on a 12-hour period. And that provides the agility the system needs to adapt to changes, significant changes in configuration and infrastructure. So provides a tremendous amount of value, but in a very short time window. When you're doing things like clustering based on temporal and linguistic characteristics, that provides considerable value, and that can be measured in terms of hours or the duration of a situation. So once a situation is over, that's it. That's your learning period closed. When you start to add human elements to it, you're really teaching the system to learn over a longer period of time, and you measure that in terms of days, weeks, and months. And finally, once that information is stored, to reuse it in the future, then there really is no long-term limit to how much value that can apply. You could potentially have a match on a situation or a cluster that was generated years from now, and be able to pull that information back and leverage the operator actions and diagnostic techniques that we use to resolve the issue in months and years from there. So very powerful indeed. Some examples. This is some research that we did polling some of our customer verticals. There's a pattern here in terms of the volume of data. Generally speaking, these metrics were observed over a couple of weeks, and the story is fairly consistent. A very large amount of data goes into the system in terms of raw events, so the raw telemetry, as it were, which generates a much smaller, usually a couple of orders of magnitude, if not more, actual unique alerts. But those alerts are still typically a very large number, hundreds, tens, if not hundreds of thousands of alerts, which is more than a human can meaningfully digest. So the clustering algorithms are intended to produce a smaller number of situations based around those unique alerts. And regardless of the inputs, we found consistently the meaningful reduction in operator workload, actionable events, as it were, is typically about 99.9%. So regardless of the input, that number was a consistent output. So what I'll do now is walk through some actual examples where we've seen this impacting real customers. So one example, fairly recent, a digital insurer, encountered this common problem of large number of data sources with an excessive number of alerts that they had to deal with. In this case, it was exacerbated by most of the systems they were using were generating email alerts, and we all get too much email, and you start adding thousands of events, just makes your inbox very messy. Generally speaking, they were dealing with something in excess of 500 events per day. They were doing manual detection, manual processing, manual triage, and they didn't really have a single pane of glass. And the reason is that they had to focus on one specific event source. They had to close down all of the other reporting mechanisms just simply to keep the number of events approximating a manageable volume. So that enabled them to, or that caused them to lose visibility across their entire stack. Here's an example of how meaningful the inbox looks. There's really no meaningful data in there at all. So the compelling event that made them rethink their strategy was a couple of operators essentially working in isolation, trying to resolve an issue. They've lost application server connectivity. Another operator is trying to identify what the importance of a network issue was. And it took them about 30 minutes to identify that they were both working on the same issue. And that's because they did not have visibility across the entire stack. So apply these technologies to that environment. The biggest single benefit is in terms of the volume reduction. Because you're reducing the volume by 99%, you can now afford to be a little bit more generous in terms of the amount of feeds that you're feeding in, giving you that full stack visibility. The correlation and producing a small number of actionable events means that the team could become more proactive, and it reduced mean time to detect. And obviously productivity increased, in this case by about 10 times. So another example from a financial organization this time, shared infrastructure. Similar story, multiple databases reporting issues. So multiple tickets were opened and DBAs were assigned to resolving the issue. This occurred because the commonality of the issues was overlooked. They were being perceived as separate issues. There was no way of associating it with probable root cause. And some unremarkable symptoms were ignored. This is what it looked like on their screen. You can see here that, this was on our screen, I do apologize. What we're looking at here is a cluster of related alerts from different databases. So the algorithms, again, it's a combination of natural language processing and time-based algorithms, identified that we were seeing similar repeated messages coming in a similar time window from databases on a similar subnet. So that amount of similarity was just too much to be coincidence. And you could actually see as well that the subject matter expert would be looking for some kind of common infrastructure, and you can see it below on the bottom of the screen there in terms of a shared file system component. Another example would be in case of a web tech provider. In this case, they implemented what we've described as cascading cookbooks. They really knew what they were looking for. They understood their environment very well. So what they were able to do is to create a sort of a sandwich of increasingly looser constraints in terms of their grouping. So they were able to correlate events by a very specific service initially. If that didn't work, you could correlate events by a partial service until ultimately you were providing some very broad groupings of alerts. The reason for doing that, the goal, the motivation, the result was to restore their single pane of glass, to once again have one place to look to identify all issues across their infrastructure. A side effect was they were able to implement collaborative team-based work processes for triaging these events, and that was enabled by the situation clustering. And the net effect, again, was an increase of capability of 10x, which was intended to meet their growth requirements. Got another example here of how machine learning can be used to detect ephemeral relationships. This particular customer has a massive array of hosted customer websites. It's all front-ended by load balancers. This is standard conventional means for providing high availability, and monitoring availability of their customer sites by synthetic transactions. It was Gomez in this instance. So I'll bring up an example here. So what they identified was that periodically customer sites were going down. But when they did some analysis to try and identify what the problem was, everything seemed okay. And the reason for this is that the issue was associated with a load balancer. And load balancers, by very definition, are non-deterministic. You can never predict the exact path an HTTP request is going to make through the network. So when they looked at our system, what they were seeing were clusters. So what we were identifying was a snapshot in time that when these particular failures occurred, there was an issue with the specific load balancer. It only took a couple of these situations to be created for them to realize the common pattern was a specific load balancer, which they took out of service. And that's a really great way of identifying ephemeral relationships. Another example would be when we talk about unsupervised machine learning yielding surprising results from data sets. As our customer were ingesting syslog events, and we were able to correlate TACACS messages with network issues. And they were able to not only identify that the issues were occurring, but identify which individual was making the configuration changes that were inadvertently causing these issues. So in summary, I like to talk about then and now. What's happened to get us where we are today? Well, in the old days, for those of us old enough to remember that, you built logic, essentially hard-coded rules to handle your environment, to which you applied your data, and hopefully you got results. And that was the process. Today, we start with the data and apply it to the machine learning algorithms, and then receive our results. The difference is, in a machine learning environment, those results can actually influence future behavior of the machine learning algorithms. That's the purpose of learning. So it becomes adaptive. The data can also influence the machine learning too, so it can become more responsive to a change in data. And finally, in some cases, the results themselves can actually form part of the data. This is something we see in production environments. And what does that mean? Well, in the old days, your logic was fixed. And if your logic was fixed, that meant your data had to be fixed. You couldn't just apply new data to existing logic because the rules would not be adequate. And your results were fairly variable. It wasn't always predictable what those results would be. Today, what we're seeing is, by definition, machine learning is variable. That means it can handle variable data sets, but your results are always fixed. So that's my summary. So I'm going to hand back now to Steve to close off.
Thanks, Richard. So yeah, just to really summarize what we've been talking through here is, believe it or not, the majority of incidents today that IT operations report are still from end users. So I'm a monitoring guy, heart through heart, and it almost breaks my heart to know that most of the incidents are not detected by tools today. And that's because of the operational noise. And just humans can no longer look at multiple panes of glass, look at the events, look at the alerts, be able to plot and chart metrics. Environments are just too big. There's too much change. There's too much technology, and that's why we struggle. And if we look at what machine learning can add to IT operations, it's really about automating all of that manual analysis. So instead of us looking at events and figuring out, hey, these are important, this should be a ticket, like we can let machine algorithms look for relationships, look for duplications, so that when we actually get incidents, there's some meaningful context there for the operators. So they can, instead of creating 100 tickets, they can create one ticket and everyone can work to solve that problem. I used to hate duplicate tickets. It was a nightmare. In fact, most of my day was spent kind of, is this a duplicate? Is it related? Is it not related? But more importantly is the anomalous behavior, right? So like, is this normal or is it not normal? An example of that is if you think about 80% of the contents of a log file is exceptions and errors that are being thrown every day, every hour, and will continue to be thrown until those exceptions are fixed. So if you have an incident or an outage tomorrow and you look and use time, chances are most of that information isn't relevant because it's normal. Even though exceptions are thrown every day, it's normal because it's been doing that for the past 5 years. So what machine learning is really good at is looking at which events, which information is abnormal, given the incidents and given the behavior of what's happening around them. As Richard said, though, I think this is a really important point. It's not a silver bullet, and you've got to relax the constraints. And I like to think of this as it's better to be right 90% of the time than trying to be right 100% of the time, because it's impossible to be 100% right all of the time. I've spent years troubleshooting production environments, and you can go down multiple paths and you can be convinced you were right on the root cause, and it turns out actually that wasn't the root cause. And it's always this strive to be perfection and to get to the root cause and really understand what went on. With machine learning, you've got to kind of almost take a step back and think, hey, if we get it right most of the time, then the times that the machine learning algorithms don't get it right, we can give it feedback. We can tell it what's right and what's wrong, and those algorithms can improve and become more accurate over time. So just bear that in mind. So yeah, I'd like to thank you all for attending. There's a white paper available of this webinar, so if you want to kind of download and get into more detail, that's available on MOOCsoft. And with that, we're going to hand over to Q&A.
Thank you, Steve. Great job, guys. Hey, I enjoyed that. I was sitting here kind of just digging into it. Again, I'll remind our listeners, we do have the question section open for questions. Feel free to type them in there, and we will get right to them. Let me go with our first question, though, and that is, I guess it's for both of you. To what extent does your machine learning algorithms adapt to work out of the box versus needing to configure and calibrate them to work in my specific or on my specific IT environment? Steve, you want to go first on that one?
Yeah, sure. So I hate to use this answer. It depends on the environment. So again, like every environment's different. And as Richard talked about, there's multiple algorithms that are applied to the processing. Some work really well out of the box. Some actually need tweaking. So it does depend on the environment. We typically see it working, I don't know, like 65 to 70% out of the box, and then the final kind of tweaking it is down to kind of making it, I guess, giving it feedback, giving it some specific kind of, hey, this is right, this is wrong. So it does depend on the environment. Richard, do you want to add anything more to that?
Yeah, absolutely. That's a really good point. We have a phase that we call calibration, and it's an interactive phase that we follow with the operators, because even the unsupervised algorithms are tunable, and the goal is to provide a series of situations that are meaningful to the individuals. And the folks who are looking at the single pane of glass are the best people to determine whether or not that's meaningful and authentic. And in some cases, operations requirements differ from definitions prescribed by system architects. So, what constitutes a valid situation in an operations context may be slightly different. So, it may be correct to say this problem has occurred, but they would like it grouped differently to match the way that they're going to go and reboot servers or make network changes and so forth. So, yes, they do work out of the box, but yes, we would also expect some kind of calibration process to make everything work happily.
Great. Guys, we've got a follow-on question to that one, too, and again, I'll throw it at both Steve and Richard. Following on to the first question, is there a threshold in terms of events per second and scale in order for machine learning to be effective? Richard, Steve?
Yeah, sure. I mean, the more events, the better. Obviously, the larger the data set, you're going to get better results. As kind of Richard alluded to in one of the slides, like if your environment's small, fairly predictable, and fairly static, again, machine learning probably isn't a best fit for those environments. The algorithms need data points, and obviously the more data points you've got, the more it can kind of understand the relationships. Obviously the less data points. So I think for me, anything like more than 10,000 events a day is typically applicable for machine learning. Anything humans can't cope with would be, I'd say, is probably the threshold.
So,
got it.
I would add to that something that I call the law of small numbers, which is, obviously the best benefit you're going to see in these environments are these massive percentage numbers in volume reduction, which means that you're doing significant amounts of clustering. But I've seen environments where the customers said, hey, Richard, there is no event volume use case here. We've scrubbed our data feed. You're not going to do anything. And in theory, to create a cluster, you could argue you need at least 2 events to group together. Otherwise, there's no clustering going on. And in that case, I would say that, well, if you clustered every single pair of events, that's still a 50% event volume reduction. So, there isn't really a minimum threshold.
Great. Next question is, and I'm going to ask Robert to jump on it, or Richard to jump on it first. You mentioned clustering a few times today in terms of what you're using machine learning for. Can you elaborate on the clustering concept a little bit more?
Okay, so clustering in our context is the technique we use to generate situations. So if you were to look at sort of a graph of the alerts as they come in, we have the horizontal axis is the cluster, and that's depending on the technique that's used. It's a group of related pieces of information, and they'll either be related by time, natural language content, some kind of external model in the form of a topology graph. The y-axis is time. So you put those two things together and you get a situation. So from our standpoint, clustering is a technique we use to group related alerts together to generate a situation.
Fair enough. Okay, our next question. How does machine learning deal with normal behavior that is not causing issues? So baseline, if you will. Steve, you want to go first on that one?
Yeah, so I think normal behavior, if you look at environments and the events and the exceptions that are thrown, they typically wouldn't have things like critical or warning or severe or fatal or words associated with abnormal behavior. Conversely, if everything's fine and you do have events that have critical or fatal, but they're thrown every single day and they're thrown every week of the year and for the next 10 years, the algorithms can actually learn and say, you know what, I see this every day, this isn't abnormal. So a lot of it does come down to like the linguistic content, the words that are associated with what the algorithms are observing. But again, if the machine learning algorithms get it wrong and detect the situation, which is kind of what an incident is, and the operator's like, hey, this isn't real, like this isn't, they can just go in and mark it and say this is not a real situation. That sends the feedback loop to the algorithms, and then things get adjusted on the fly.
Okay. Let's see if we have our next question here. How are you able to correlate between the virtual software and the physical infrastructure layers below if you don't have access to asset configuration database, or do you require that access? Richard, I didn't give you a chance to answer the last one, so I'm going to ask you to go first on this one.
That's a tough question.
And so we got the move from Moogsoft, but go ahead.
There we go. So that's my cue to ruminate for a second.
Okay.
So that's basically where this notion of relaxing constraints comes in. So obviously, you know, in an ideal world, you would understand the relationships, either because you've had the time and opportunity to model them in your CMDB, or even more perfectly, that CMDB is being driven on demand by the provisioning solution. The reality is that's not true. We have at least one customer who told us that anybody whose CMDB is more than 35% accurate deserves some kind of medal. So that said, how else can you make those relationships? And that's where being data-driven comes in. You can really help yourself by providing significant information in the data stream. We're seeing that a lot in newer environments such as OpenStack, where they're extensively making use of the technique known as tagging, where you can put labels in the raw data that can be used for correlation upstream. But as the information becomes scarcer, you relax your constraints and you start to leverage the more unsupervised techniques. So ultimately, your catch-all is time. You know, if two things complain at the same time, they may very well be related. But this goes back to the layered approach. Reliance on one technique alone may yield unanticipated results, but you apply multiple techniques and you're really going to focus in on the issue.
Fair enough. Next question. On one of the slides in the middle, and of course I don't have it in front of me, you list the different tasks that machine learning can help IT teams with. Are the different machine learning algorithms more suited for one or more of these tasks than others?
Yes, I think I know the slide you're referring to, and yes, you know, the answer is, you know, obviously if your interest is in, you know, some geolocation was the example I think I might have used earlier, then you're going to be using something like, you know, sort of a semi-supervised technique where you're applying your clustering algorithms to very specific labels and specific areas within the data. You know, you might be looking for the 3-letter NFL city acronym, like you know, SFO or NYC or something like that, and that might be everything you need to generate meaningful data. If what you're looking for is that elusive needle in a haystack, and you have a vast amount of data coming from an application log or something, and you just want to look for the anomaly, then you would probably be using some kind of you know, technique such as significance detection, where you're using the natural language and the temporal anomaly detection. So yes, it really depends on what you're looking for as to which specific technique you apply.
Excellent. Okay, we only have another 2 minutes or so, so this may be our last question. What source of the alerts can be integrated with Moog source? So, for instance, can EMC smarts be integrated? MSSEOM, syslog, traps, etc.
Yeah, it's a popular question. So the short answer is anything, because we use natural language processing, or should I say most machine learning algorithms rely on natural language processing. So it doesn't matter the structure, the kind of syntax, the words that are used. As you saw, Richard actually ingested tweets. So for example, MoogSoft has over 100 integrations with kind of New Relic, AppDynamics, Splunk, syslog, VMware, all of the common kind of event sources that a typical customer might have. Where there isn't support, we have a JSON REST API, so you can just pump in the events, the alerts through a REST API. And again, the machine learning algorithms will tokenize it, they'll analyze all of the structure, the text, and Bob's your uncle, as we say in the UK.
Okay. Guys, at this point, we are just a minute or so before the top of the hour, and we're respectful of people's times. And we thank them for taking an hour out of their day to spend it with us. Steve Burton, Richard Whitehead, MoogSoft, thanks so much for delivering a great webinar today. MoogSoft, thank you for sponsoring today's webinar. And most of all, to our attendees, thank you for voting by choosing to attend today. And we hope you found it interesting. This is Alan Schimmel for DevOps.com, and we hope to see you again at a webinar soon. And again, just for may come up a question, a recording of this webinar, slides, questions, will be available on the site within 24 to 48 hours. And finally, you can request a trial and get started by visiting moogsoft.com. It's up on your screen. Thank you, everyone. Alan Schimmel for DevOps.com. Have a great day.